Here we go. So today we're going to be doing a little more of Stokes' theorem, more of this stuff with the curl, more path integrals. So it's going to be a continuation of yesterday. All right. So I want to remind you, remember that what the Stokes theorem told us from Wednesday was that if you have a single work integral, you could equate that to a double integral of stuff happening on the inside. So let me fill in the pieces. On the left, you're doing a work integral of some vector field along a curve. So this is like as you move along some, I'll draw this right here. This is some curve C. You move along C, and you're seeing, on average, you know, is the wind pushing or pulling along that direction, along that curve? Like, did it help you do any work? If it helps, I was biking a couple days ago, and I kept thinking about this. You know, when you're a biker or a runner or a swimmer, or I guess, or even someone who's flying an airplane, you know, when you're doing a loop and maybe you're trying to get a really good time, you might wonder to yourself, will all, and you're fighting the wind at some point, your brain will naturally start to think, you know, will the wind help me back at some point? Like, if right now it's hurting me, maybe at this point the wind is going against your direction, but can I find a spot where it helps you out? But maybe back here it was pushing you in the correct direction. So is the overall net effect a positive effect, a zero effect? You know, that's kind of one way to think about what this integral measures around a loop. So, and then Stokes' theorem says that if you want to figure out what this dot product is, you can also, you go inside the region that you filled up, and you can integrate the curl on the inside if you wanted to compute this a different way. Okay, so this is what we were exploring last time. And this is the caveats were C is oriented counterclockwise about the region R. This is its interior. This is the interior of the loop encompassed by C. And the other thing is that you really need that the vector field to be defined in the entire region of R. And then V needs to be defined on the entire interior IN of R. Like, there can't be one single point where it's not defined. So we'll explore that later. But I want to, before we do a few more examples of this, I want to ask or kind of hint at, why does this work? Why is this true? And to answer that question, I'm going to tell you, I haven't really told y'all what curl intuitively measures. So I'm going to try to discuss what curl is to answer, what does curl of V measure? Okay, so let's take this to this next page, and then we're going to talk about what curl actually is telling us. Oh, and something that's kind of cool, the president of the college will be sitting in on one of our lectures on the 20th. So that is not next class period, but 4 class periods from now. So that's pretty cool. We'll talk more about that later, I think. Okay, so let's recall our favorite 2 vector fields. The radial vector field, so V is x comma y, and over here we're going to have V is negative y comma x. This one was our standard rotational, and this one was our standard radial. Just to draw them out, they do something like this. And this one kind of spins about counterclockwise. And when we first discussed curl, we computed that this has curl of V is 0, whereas this has curl of v equals 2. So the idea is that curl of v at a point x, y measures the uh, rotation of the vector field at that point. It's kind of put in another way is if you had a pinwheel is something that spins left and right and it catches the wind. If you could plop a pinwheel at a point, what curl is measuring is it's saying how much would it start spinning. So if I place a pinwheel at a point xy, then curl of v will tell me how much the pinwheel rotates at that point. So positive curl means counterclockwise rotation of pinwheel. Zero curl is no rotation. And then negative curl is clockwise rotation. So that kind of makes sense. I'm going to zoom in over here. Well, I guess some of y'all might be writing. If I zoom in at this point and I put a little pinwheel down, like the wind is going to start pushing it. The wind is going to push the pedals up here. And the wind is stronger at that point than it is this point because the arrows get bigger as you get further out. So the little pinwheel is going to start spinning this way. However, if I placed a pinwheel right here, okay, then the wind that pushes it on this side, well, you might think, all right, well, it's going to start spinning this way. But no. There's also wind pushing these pedals. So the pinwheel itself kind of gets stuck. Okay, and so this one has every point the pinwheel would not spin, but in this vector field, it will always make a counterclockwise rotation, and that's what curl is telling you. Okay. I'm gonna say be careful, so beware. Your eyes can deceive you. I before E, C after C. Yeah. Okay. Okay. Because let me cook up an example of a vector field, a pretty basic vector field that doesn't look like it's rotating at all, but it actually is. So let's do the vector field v of x, y is equal to just y, comma, 0. Okay, let's look at this for a second. I'm going to plot what this vector looks like. So the 0 and the y in the second component of the vector means the vector will always be just pointing to the left or to the right, never up and down. And this is telling me when I'm higher up, when my y coordinate's higher, that means I'm moving to the right more. And when I'm down here, that means I'm moving to the left more. So the vector actually looks something like this. All right, so this is what a plot of the vector field kind of looks like. You might think to yourself, it kind of looks flat in some sense. It doesn't look like there's any spinning. It doesn't look like a hurricane's wind or a tornado's wind or anything of the sort. And let's go ahead and compute curl. Let's see if there actually is any rotation. So the curl of v is going to be partial x, partial y, and 0. We take the determinant of this. Here I'm going to get 0 minus 1. So I get -1 curl. So you're thinking, what? This is rotating? How so? Okay, well, if you can convince yourself, let's like plot a pinwheel at some point. So let's plot one right here and I'll put the fins on it like this. Okay. So, like, yeah, these two legs are getting pushed on, but up top, it's getting pushed on harder than it is on the bottom. So overall, the vectors up top are pushing harder, and we get clockwise rotation of the pinwheel. So that's just something I wanted to say. So this has curl. Okay. And let me do a second example of something, how your eyes might deceive you. So this was the picture of, doesn't look like it's rotating, but actually it is rotating if you do the math. Here's a counterexample. So an example where it looks like it might be rotating, but if you actually sit down and do the math, it's not. So let's do v of xy. And I've mentioned this a couple times before, and this is going to be a really fundamental example. So I'm actually going to pull out the constant. So it's 1 over x squared plus y squared in a square root that times negative y comma x. So you know, you can factor out scalars from a vector, and that's what we're doing. This is a scalar. The scalar that changes from point to point, and this is our rotational vector field. So this vector field is going to look like the rotating one. The rotating one typically does this thing. It's got a, I've drawn on the previous page. It's rotating, and the and the vectors get bigger as you move outwards. That's not what's happening here. The factor in the front kind of makes everything of unit length. So the vectors are rotating, but they all have length 1. That's kind of the effect that you get by taking the by normalizing it or making it of length 1, the vector field. And so now you're looking at this thing and you're saying, yeah, that thing is definitely rotating. But the problem is if you actually plot, if you drop a pinwheel at a point, let me zoom in, see what happens. If you drop a pinwheel, then because everything's unit, the vector that's pushing on this leg is the same length as the vector that's pushing on this leg. And so the effect of the pinwheel, it's not going to move. So this, in fact, deceivingly has curl 0. Deceiving, this has 0 curl. And either we're going to do that computation today, or it's going to be on homework. But definitely to see that this thing is curl free, it's an important exercise. But just the derivatives kind of suck because you have to do that, the square roots and all those things. Okay. Oh, I'm seeing some chats now. Is that true even at the origin? Okay. Okay, so at the origin, the curl isn't defined. So yeah, so curl of v at 0, 0 is not defined because the vector field must be defined at the point. So that's a good thing to notice. Yeah, the problem is that we are dividing by 0. In essence, it's sort of like we're storing all of the rotation at the origin. And then Kelly says, does this relate to the idea that there can't be a whole? Yes, this is precisely the idea. There's really something funky going on. The fact that we're dividing by 0, and we'll either at the end of class today or on your homework somehow I'll sort of explain that really this division by 0 makes something weird happen. Okay, so I actually haven't even explained why Stokes' theorem even works, or roughly why it works. I mean, the idea for why does Stokes' theorem make sense? Well, if you start plotting a bunch of pinwheels next to each other, and that's, at each point you're measuring the curl. I mean, maybe here you're going to have positive curl, and negative curl. So still on the whole, if you're integrating, it would be positive because there's some cancellation. So you're sort of you'd be seeing pushing forces happening this way, yet pushing forces happening clockwise around this buddy, that one. And then up top, you'd have clockwise forces going around this pinwheel. And so on the whole, if you sort of aggregated everything, pushed everything together, you'd get a small clockwise rotation around the full thing. And let's say you want to add another pinwheel. So that was 1, 2, 3. Let's put, you got another pinwheel right here, and it's super negative. So this pinwheel is really going clockwise. Then by the time you sort of encapsulated that one in the full curve, none of this is precise at all. This is kind of what you're feeling in your bones. Maybe that has the effect of canceling what you've got, and this makes the out curve at the end going, should be clockwise. That's kind of the picture. The idea is that you're kind of pushing all the internal stuff into outward forces happening on the edge. So that's kind of why the integrating the internal rotation on R is sort of like doing the external forces on the boundary. Anyway, that was my long-winded 16-minute explanation for why Stokes' theorem works. But okay, we really haven't done any math so far. Well, I guess we did some derivatives, but let's do another example. Okay. Okay, let us do an example. All right, let's do the integral. It's a work integral of v dot t ds over c. C is, I'm going to say clockwise unit circle centered at origin. And v is the radial vector field, x comma y. So there are going to be two different ways to see that this answer is 0. So this value, this is 0. So we can see it in two different ways. Okay, approach 1. If you plot it, then the vector field, okay, we know that this is our friend, that radial vector field. And as we go clockwise around this thing, if you notice at every single point, then the purple is making right angles with the path that we're making. So along C, we know that the unit tangent vector is always orthogonal to V. So T dot V is 0. And so the integral of V dot T ds is the integral of 0 ds. Okay, so that's the easy way. We didn't even have to do any parameterization. And the approach number 2 is to use Stokes' theorem. Approach number 2, oh my gosh, that's messy, is Stokes. And so Stokes' theorem says that the single integral of v dot t ds should be equal to, and be careful what I'm doing, is equal to the negative double integral of r over r, where r is that internal disk. Okay, that's r. Of curl of v dA. Now, can anybody tell me why, anybody guess why I included the negative right here? What's different about this that required me to use a negative sign? Clockwise, yeah, good. Yeah, so because I picked the clockwise unit circle, my orientation of C doesn't quite agree with the orientation of the internal object. So just to correct that, I got to slap a negative on. So I wanted to show that at some point. But in this case, it's really not that big of a deal because we've already computed that the curl of that vector field is 0. Okay, and also we're also allowed to write this equality because the vector field in question, there's no division by 0. There are no domain issues. So we're seeing this is the negative double integral of 0 dA, so that's just 0. Okay, cool. All right. So I was going to do another example, but I think at this point, there are bigger fish to fry. So All right, I'm going to flip the page. And we're going to move on to the fundamental theorem of path integrals. Okay, so now, what was that? That was page 4. Here's page 5. So now we'll be working on the fundamental theorem of calculus. Okay, so this is going to be very similar to stuff that we've done before, but now we're just going to go back to the case where our paths kind of looks like this. Okay, so our path starts at point A, it walks around and it goes to point B. Okay, that's our C. And then we've got some vector field hanging out. And we're interested in computing v dot t ds over curve C. Okay, all right. So so suppose we're in the very special case. So suppose we are in the case that v is conservative and has a potential function. I promised that this was going to be important at some point, and so today's that day. So remember, having a potential function just means that v is the gradient of f for some f. Okay, so let's explore the value of that integral. Okay, so the value of the work integral is an integral over c. This is v dot t ds. And so now if I know that v is a gradient vector field, I can replace it with that. I can replace v with a gradient. So this is an integral of the gradient of f dotted with my unit tangent vector ds. And now I'm going to unpack this. So now say C is parameterized by some R of t, where t is from A to B. This is always how you actually set these integrals up. So it's an integral that ranges from A to B. And I'm taking the gradient of f, and I'm dotting it. Well, I guess I can write gradient of f at R of t. I'm taking that dot product with R prime of t dt. Okay, that's always how these things boil down when you set up the integral. So I'm going to invoke something that we've discussed a long time ago, but this is a very special thing right here. This should remind you of the chain rule, what we did before midterm 1, actually. This was before midterm 1. So the chain rule says that this equals, if I basically took a derivative, so oh goodness, this is d dt of f of r of t. So remember, okay, so I'll write it again for people who don't remember, but this is the following: f of t dotted with r prime of t. So it's saying that, okay, remember, you've got some function and you're composing it with a path and you're feeding it time value. So this is a function. It takes in one number and it spits out one number. So you can take d dt of it like you're in calc 1. It takes in one number and spits out another number. But if you also want to find another way to write it down, is that this thing right here on the right hand side is the dot product of two vectors. So this is just trying to remind you of what this thing says. So I'm going to say this integral is the integral from a to b of d dt of f of r of t dt. Okay, And this, I mean, if it helps you out, you can call this thing, you can call this g of t if you'd like, just to make things simpler. But because, and remember, in Calc 1, you learned that the integral from a to b of d dt of g of t dt, you saw an integral of a derivative. You can just undo both of them. This is just g of b minus g of a. This was Fundamental Theorem of Calculus in Calc 1. So if you come back over here, that's exactly what we have. So the final answer is this thing should be equal to f of r of b minus f of r of little a. And you're like, what is r of at these values? Well, here, this is my final value. This is r of little b, should be equal to big B, and r of little a is equal to big A. So the final answer is, this is just f of b minus f of a. And then Daniel asks, is the dot product with r or with the derivative of r? Thank you, Daniel. Yes, yeah, that should have a prime right there. Thanks. And good, I included the prime right here. Good. Okay. So I'll write that I'll copy that and write it on the next page and show and we'll do an example of this. So to summarize, when the vector is equal to the gradient of some function, and C is a curve in the domain of f and v, then the integral along C of v dot t ds just equals f of b minus f of a. Okay, and it's one way to think about it is it's sort of like if f is describing like some hills, okay, and you're going for a run and you want to know the gravitational work that you've done, then so if f represents like the hills or some landscape, and C represents the path you take on a jog, then C of gradient f dot t ds is the gravitational work you do. This is the gravitational work done. So if you have motivation from physics, if you know anything about physics, this is just equal to the height displacement. Like it's your altitude of your final minus your altitude of the initial. So that's like another way to look at these things. And the conserved quantity along your path is the height. All right, so let's do a neat example. Okay, so let's do an example. This was a problem that came from actually the homework that is due today. It's the it's the problem that I took off. So the problem asks to do the following work integral, and it says v is equal to this. Okay, v is equal to y squared plus 2x e to the y plus 1, comma, that's the x component, 2xy plus x squared e to the y. I mean, you're already seeing that this is a total pain in the butt. I mean, it's nasty. And then c is is a quarter of a circle. It goes from here to here, unit circle. Clockwise, and here's my c. Okay, so if you actually if you want to just muscle through it, and you set up the parameterization and you set it all up, you get an integral that's just really hard and nasty to do. But the trick is, I don't want to say trick, but the nice thing is to notice that this does come from a potential function. So when, like, a good rule of thumb, whenever you start to do any work integral like this, the first thing you should do is check the curl. If the curl is 0, then you have a chance of finding a potential function. So I always just step 1 to investigate, check curl. Okay, so we're gonna do d dx, d dy. Ooh, I've got to write all this down again. Okay, so we got y squared plus 2x e to the y plus 1, 2xy plus x squared e to the y plus 2y. Okay, so I'm gonna do this derivative, so then I'm gonna subtract that derivative. This gives me 2y plus 2x e to the y, okay, plus 0, then minus, all right, 2y plus 2x e to the y plus 0. Okay, and then check all those things cancel out. So that's 0. Nice. Then we have the possibility of actually finding a potential function. So curl equals 0. Let's find a function f of xy. So, okay, this is page 5, this is page 6. So, and I am just going to say what a potential function could be. So, one potential function that works is f of x comma y equals, I did it last night. Okay, you can do this. Y squared x, I couldn't do this just by looking at it, plus x squared e to the y plus x plus y squared. You could also add on any constant you'd like 7. Yeah, I'll go back for a second, Kelly. So, okay, that's the potential function that I came up with last night. So Kelly has to go back. So here's the previous page. And so basically the steps, yeah, we did the curl, we found out that it was 0. So now that we know it's 0, we think to ourselves, ooh, maybe we can find a potential function. And you can, and I believe all of y'all could do this. I did this on my own last night by taking 2 integrals, and I kind of reverse engineered what it would have to be. But you could even check, I mean, to check if your answer is right, you can always just take the gradient. So to check if this f works, you could just do the gradient of f and see if you get the original vector field. So let's just check really quickly. You get y squared plus 2x e to the y plus 1 comma 2xy plus x squared e to the y plus 2y, and I believe that's exactly what the book gives us. So yes, this equals v. Okay, so instead of having to do all of the nasty work, instead of doing this c v dot t ds, which is a pain, all of these sines and cosines, do you believe that you're going to have like sines and cosines times exponentials of sines and cosines? And if you remember anything from Math 102, those are supposed to make you cry. That's the only reason why they exist in math. It's just to make people, to make 102 students sad. So let's not do that integral, and let's actually just say, so this is by Fundamental Theorem of Calculus for path integrals. Well, this is just f of my final point of, I guess, of f of b minus f of a. And I'll remind you what the curve was. This was this curve right here. So this was my b, this was my a. B is 1 comma 0, a was 0 comma 1. And so if I plug all that stuff in, I got f of 1 comma 0 minus f of 0 comma 1. Okay, now I gotta plug this stuff in. So I'm plugging stuff up here into that purple. That's what my f is. If I evaluate it at 1, 0, okay, it only sticks around if it doesn't have a y. So I've got 0 plus Okay, I guess that's 1 plus 1. Yup, and then minus 0 plus 0 plus 0 plus 1, so it should just be 1. And that's a lot easier than this. Okay. Let's see. Anybody has questions? We can do this again. We'll do another example. So let's do another example. Let's do a work integral of v dot t ds over c, where c is the spiral given by r of t equals e to the t cosine of t, e to the t sine of t, where t ranges from 0 to 2 pi. So I'll sketch that for you, and I still need to tell you what the v is. So it looks like a circle, but the radius stretches out as you move in time. So it spirals out like this, okay? Where my initial point is here, A is, I think, 1, 0, and then my final point is B, which is 2e to the 2 pi, comma 0. Okay, and then my vector field is going to be my radial vector field. I'm just going to do 2x, 2y. If I just rescale a vector field by a number, I just make the vectors bigger at every spot. Okay. Okay. Do people remember, does anybody remember that v is actually the gradient of some function f? Can anybody remember what function gives this vector field as a gradient? It was probably all over the exam, if you remember. What is this? Does anybody remember what makes this? Yes. Okay, good. Yes, good, Leanna. Okay, so I included the 2 so that y'all wouldn't have to do the 1/2, but that's exactly right. So Leanna said it correctly. So v is the gradient of f, where f is x squared plus y squared. Exactly. It's that radial thing. Good. So the 2 comes down as from the power rule. Exactly. So instead of having to do this setting up this integral, plugging in the dot product and doing things, you can actually just write that the work integral is I'll write it, you're integrating along C, you're dotting your gradient with your unit tangent, and this just turns out to be f of b minus f of a. And so this is, I guess, okay, got to plug in these 2 points into the function that Liana suggested, this one right here. And what do we have? This is, okay. This is e to the 2 pi squared plus 0 squared minus 1 squared plus 0 squared. And so at the end of the day, I get, I think, e to the 4 pi minus 1. Is that good? Okay, I got that yesterday. All right. So the main idea is that if you can notice that your gradient, that your vector field is a gradient, you can save yourself a lot of work. So I'll write kind of a little summary over here. I'll say, rule of thumb. Whenever asked to compute a work integral, always check if the curl of v is 0. Okay, so if curl of v is 0, then look for a potential function. Okay. All right. All right. All right. All right. All right. So here, probably for the last 10 minutes, I want to talk about the vector field that I keep on bringing up. So the last 10 minutes, we'll discuss this vector field. So v of xy is, all right, it's negative y over x squared plus y squared in a square root, and x over, actually, I don't think I need to take the square roots, but that's fine. Okay, let's do this. Okay, so the domain of v essentially is you can plug in any point you want in the xy plane, but you can't plug in the origin. So the domain basically has a hole. Okay, so not simply connected. Maybe we'll talk about what that means a little bit more later. But let's just show that you really can't use Stokes' theorem the way you'd like. So let's see why we cannot use Stokes' theorem. Okay, so I'm going to tweak this a little bit. I'm going to get rid of those square roots. You can do it with or without them. And for this example, so it's negative y over x squared plus y squared, and then x over x squared plus y squared. This is going to make taking the curl much easier. Okay, so I'm going to move on to, so this is page 9, so page 10. Okay, so we're going to investigate why that v dot t ds is not equal to the double integral over a region of the curl of v dA. Okay, where c is the counterclockwise unit circle, and then r is inside of that. Okay, so let's investigate the double integral first. So investigate the double integral of the curl of v. So we have to compute the curl, so let's do it. This is partial x, partial y, and I've got negative y over x squared plus y squared, and I've got x over x squared plus y squared. Okay, if I start taking this curl, it's kind of gross because I've got product rule, but I believe we can do it. So it's going to be, I'm going to first do that x derivative. So it's low d high minus high d low all over low squared. So I'm just going to write that all over low squared at the bottom first. Okay, so we've got to do low d high minus high d low. So I've got low times d high minus high d low. So high is x and d low is 2x. And that's all over low squared. So now we're going to subtract if we do the same thing with the y's. So it's also going to have the same denominator, x squared plus y squared squared. And let's see what happens. So it's low d high. So it's x squared plus y squared. But d high is negative 1 minus high, which is negative y, d low is 2y. And I'm just going to write the same stuff on the denominator. If you'll see cancellation happens, essentially. You get x squared plus y squared minus 2x squared plus x squared plus y squared. Oh gosh, how many minuses do we have on the third one? So we'll have a minus 2y squared. And you can see that you'll get cancellation on the top because I'll circle my x's. You got 0 of those, and I'll circle my y's. Okay, so that's 0. Okay, So, so you're getting that it doesn't have any curl. So I'll move to this next page. This was just kind of computation. I really should get better at writing smaller. So it's just page 10, so page 11. So if you did want to do the double integral of the curl over the region R, you're basically just integrating the constant function 0 everywhere except that little point. And so you'd be integrating, you get 0 at the end of the day. If you did want to do this integral, okay? On the other hand, let's actually set up the parameterized integral. So let's set up r of t is cosine t sine of t. And we know t is ranging between 0 and 2 pi. This is going to give us that circle that I'm discussing. This gives us c. So if I actually want to do the integral, I'm going to be doing an integral from 0 to 2 pi. Now I've got to evaluate my vector fields. So let's evaluate this. This is I should be doing negative y over x squared plus y squared, but I got to plug in what I have around my parameterization. So this is really negative sine of t over cosine squared of t plus sine squared of t, comma. All right, now I need my x over x squared plus y squared. This is cosine of t over cosine squared of t plus sine squared of t. Okay, that was my v. Now I'm dotting it with r prime. So r prime is, I gotta take the derivative of this. So that's negative sine t comma cosine of t dt. Okay. Well, as you probably can see, those denominators clean up quite nicely to just be a constant clean 1. And we're really doing the integral from 0 to 2 pi of sine squared of t plus cosine squared of t. This is after doing the dot product and cleaning up those denominators. And so now you can see this is the double integral of 1 dt, and that is equal to 2 pi, which is not 0 up there. So something funky is happening. Somehow, so Stokes' theorem doesn't apply to this situation. So thus, Stokes' theorem does not apply here. And there's kind of a reason for this. So the reason why, like I only have a minute and a half left. So actually I go back here. It's kind of all over the place today. Didn't have much time to prepare actually, because I spent a lot of time trying to kill the cockroach in my apartment. So I apologize that I've been a little bit, I've been trying to catch up with my notes because I thought I would have more time to prepare this morning. But the idea is that this function, where's the original thing that I drew? Where is it? Okay, this thing right here, this vector field, yeah, it is curl free. And on certain parts of the plane, you can actually find a function that has this as its gradient, but it's not defined everywhere. In fact, the actual function that you would describe is the angle function, and the angle function is only defined as a continuous function at certain, like, you can't continuously define it on the full plane, because like at this point would simultaneously have theta equals 0 and theta equals 2 pi. So there's something that's funky going on here. So in fact, you can cut up the region into these different squares, which we'll discuss at a later time. But anyway, I'm kind of all over the place, but that's all we have today, and I will stop recording. And oops, you can ask questions. Let me go back to that. Shoot.